Alrighty folks, so in our last video we discussed some diagrams and graphs, and we specifically looked at position versus time graphs and velocity versus time graphs. Now let's look at some special cases because we're going to do a lot of problem solving once we finish off our notes, and there's sort of two regimes that we're going to try to identify. One is constant velocity and the other is constant acceleration. So let's look at some graphs of both of these, and then we'll consider the equations that go along with each of these regimes that you will be using to solve problems. All right, so first let's look at constant velocity. If our velocity is constant, well, on a position versus time graph, slope is velocity, and the slope should not change if the velocity is constant. If the slope doesn't change, that means that we have a straight line. So if you have constant velocity, it will look like a straight line on a position versus time graph. If we were then to plot velocity versus time, a constant velocity situation would look like a perfectly flat line. We would be at some velocity, and it wouldn't be changing. We're happy right where we're at, whatever velocity we have, and it doesn't change, so it just gets carried straight over. As time goes on, it doesn't change. Well, we do have a slope here, and we can interpret that. As time goes on, if we have constant velocity, we move to the right, but our position is changing, but it changes nice and steadily. As time goes on, we cover more and more distance in equal amounts so that we get that nice straight line. Well, now let's consider constant acceleration. In a regime of constant acceleration, your velocity is always increasing. If your velocity is always increasing, well, the slope of a position versus time graph, which is given by velocity, should always be increasing. So it might start off low, but as time goes on, that slope, which can be found by drawing sort of a tangent line, a line that just barely touches the graph, we can see that the slope goes up and up and up and up, forming a sort of curve. We'll find out when we look in this in a little more detail that that's actually given by a parabola. All right, well, what does a velocity versus time graph look like if we are undergoing constant acceleration? Well, we know that the slope of a velocity versus time graph gives us acceleration, and if it's constant, the slope should never change, which would mean it should be a nice straight line. And if we interpret that, constant acceleration means our velocity is always changing, and sure enough, as time goes on, that velocity just goes up and up and up and up. And those are just a couple of simple situations to consider to understand what these things are going to look like, what sort of shapes of graphs to expect in the basic graphing of position versus time and velocity versus time. Now, for both of these, we also have a set of equations. Our constant velocity equations I've written here, and our constant acceleration equations I've written here. And I'm going to talk through them now. Now, whenever I like to look at equations, I like to think of them as telling a story. So for instance, over here, under constant velocity equations, let's look at the first one. It's our distance formula. It says the final distance, the final position, is given by the initial position plus your velocity times time. So your final position depends on where you start, and then you add on how fast you're moving and for how long. That is sort of the story of where you went. You know where you ended up by looking at where you started and then adding on how your motion changed that. And alternatively, we could move this piece over. If you subtract that d0 over d0, we have d final minus d initial. We could just call this displacement equals velocity times time. How much your position changes depends on how fast you're going and for how long. And also in what direction, because that really is velocity. So how your position changes depends on how fast and in what direction times how long. And really, I've got two more equations here, but they are just this exact same equation rearranged for the different variables you might need to solve for. So you could find the displacement by multiplying velocity and time, or you could find a velocity if, for instance, you knew your displacement and the time it took to make that displacement. And lastly, you could maybe compute the time for a trip if you knew how much your position's going to change and you know what velocity you're going to be traveling on your way there. I like to try to tell stories. It makes equations a little more lively. They're not just numbers you plug in to get an answer. You're telling a story, and you want to see if your story makes sense. Once we start problem solving, I'll really emphasize checking your solution, asking if it makes sense before just writing it down and moving on. All right, well, these are situations for constant velocity. For constant acceleration, it gets a little bit trickier. We have a couple of more complicated equations down here that we'll get to. But as it starts off, we have some very similar looking equations. Here we have velocity, and we can find a final velocity by looking at our initial velocity and then how our acceleration changes it. So your final velocity is equal to your initial velocity plus how you're accelerating. And remember, direction matters here. You could be negative and take away from this value, or positive and add to this value. And of course, for how long you accelerate. We then have the definition of acceleration itself here. Acceleration just is defined by the change in velocity over time. And this comes from the previous equation. Again, we could subtract that piece over, and we would have final minus initial velocity, which is just change in velocity. Your change in velocity defines your acceleration. All right, now there's some math we can do using these equations and the average velocity. When you're under constant acceleration, there's a special equation for average velocity. You can plug it into here, do some fancy math tricks, and you can find a distance formula for constant acceleration. The distance formula would look like this. Your final position depends on your initial position plus how fast you are initially moving, plus a term that involves your acceleration and time squared. So where you end up depends on where you start, how fast you're moving, and how you're accelerating. And again, if we wanted to instead represent this with displacement, we could move that initial over, subtract that piece over, and we have displacement equals v naught t plus 1/2 at squared. Now lastly, this is a really cool equation because there's something special about it that the other ones all have in common that this one does not share with them. And that is it doesn't involve time. Now there's some fancy math tricks using substitution where you remove or eliminate the variable of time. So instead, all this one cares about is you can find your final velocity if you know your initial velocity, how you accelerate, and for how far you accelerate. Rather than looking at how long you accelerate for, instead you can use how much displacement you are accelerating for. So for what amount of space you are, hitting the gas or hitting the brakes, that can explain what your change in velocity is going to be, what your final velocity will be. And I usually like to number these equations 1, 2, and 3. And we'll get back to this when we get to problem solving. I have a simple flow chart for this chapter that will allow you to quickly figure out which of these equations you can use to solve a given problem. All right, now there's one more thing I'd like to look at before we finish off this chapter, and that is the acceleration of gravity. So we've talked about position, velocity, and acceleration. One source of acceleration, in fact a very common source, is that of gravity. You guys have felt it every time you wake up, it's there. You go to sleep, it's still pulling on you. You try to jump, it pulls you right back down. Gravity pulls everything towards the ground. And it pulls everything in a way that accelerates it at a rate of negative 9.8 meters per second squared. Now this is the acceleration of gravity. In chapter 3, we'll cover the force of gravity. Force is actually different than acceleration. As we'll later see, force is what causes acceleration. But don't refer to this as the force of gravity. Negative 9.8 meters per second squared has units of acceleration. This is the acceleration of gravity. And it's typically given by the lowercase letter g. So the acceleration is g, which is negative 9.8 meters per second squared. Things get accelerated downwards in a gravitational field. So let's consider this example of tossing a ball in the air. I have a nice little diagram here. This is a motion diagram like we looked at earlier. And on each individual image for the motion diagram, I have also labeled vectors. I've drawn arrows on there for velocity and acceleration. When you throw this ball up in the air, its initial velocity is upwards, and it's probably going to be pretty fast upwards. That's why I've drawn this arrow a little bit longer. The length of these arrows indicates the magnitude of the vector, in this case the magnitude of velocity, and the direction, of course, is also part of that vector. So initially you throw the ball upwards, its velocity is upwards, but gravity's always pulling it down. So after another moment, velocity is upwards, acceleration is downwards. It's going to cause it to slow down. So sure enough, by our next image, the velocity vector is shorter. We have less velocity, but what's going on with acceleration at this point? Still pulling down. Negative 9.8 meters per second squared. Gravity's always pulling you down. So after another moment, and you can see I've tried to indicate in my spacing, it covers less vertical distance because its velocity is less. But by the time another moment has passed, that velocity is getting pretty small now. Very little velocity, still upwards slightly. But what's acceleration doing? Still straight down. Gravity is always pulling downwards. At the very peak, for a brief instant, that velocity is zero. The velocity is zero right at the peak. But what's going on with the acceleration? Still pulling it downwards. Gravity's still pulling that ball downwards. Well, if the velocity is zero, and it's being accelerated in the negative direction, sure enough, that velocity now becomes negative. A moment later, it's been pulled into the negative direction. Velocity started upwards, acceleration was opposite until that arrow shrunk and shrunk and shrunk to nothing, and now gravity begins pulling it downwards and increasing its velocity, but in the negative direction. And at this point, those arrows point in the same direction. Velocity is downward and acceleration is downward. So it's going to begin speeding up. So in the next step, that velocity is a little bit bigger. Acceleration is still downwards. They're still in the same direction. So as time goes on, that velocity gets even bigger. And acceleration is still pointing downwards. Throughout this entire process, our velocity changes, but the acceleration is constant. The acceleration is g, which is negative 9.8 meters per second squared, always. The acceleration is always downward. The velocity changes. Velocity starts by being thrown upwards. It has an upward velocity, but with acceleration downwards, that velocity is going to shrink and shrink and shrink until it becomes zero, at which point gravity begins accelerating it in the causing its velocity to become negative. And once its velocity is negative and the acceleration is also negative, we see it speed up. That velocity vector gets bigger and bigger, but in the negative direction. So even though you might have your intuition tell you otherwise, that maybe at the top while it pauses briefly, that maybe it's no longer affected by gravity, That is certainly not the case. It is always, always, always affected by gravity. Always negative 9.8 meters per second downwards. And we can see in this example the great interplay between the velocity vector and the acceleration vector, and how acceleration affects that velocity vector. All right, that does it for our notes on Chapter 2. We will now begin to cover some examples and really get to see this stuff in action. And I feel like that is whenever you will really begin to have a strong understanding of this material. So I look forward to working some examples. I will probably post some of those for you guys to follow along with as well. Until next time, see you guys later.